In this video, we're going to talk about what happens when we take the quotient of a ring by a maximal ideal. So let's start with a couple of examples. In the previous video, we saw that Z has, among other ideals probably, the maximal ideal the principal ideal generated by 3. Now what happens when we take the quotient of Z by this maximal ideal? Well, to figure out the structure of this quotient ring, we need to think about the congruence classes of integers modulo this ideal, which is really to say the congruence classes of integers modulo 3. The cosets of this ideal are 0 plus the ideal. That's just the set of all multiples of 3. And then another coset would be 1 plus the ideal. That would include such integers as -5, -2, 1, 4, 7, and so on. And then there's also the coset represented by 2. And that includes things like -4, -1, 2, 5, 8, and so on. And if you look at those three sets put together make up all of the integers. So what I have here is a quotient ring where the integers have been divided into three cosets. There's the ideal itself, there's this coset, and there's this coset. So 1, 2, 3 elements in the quotient ring, because in the quotient ring each coset counts as one element. 1, 2, 3. And without doing too much more work, you can discover that this quotient ring actually has a familiar structure. It's Z mod 3. In fact, again, really what's going on here is Z mod 3 has exactly the same, not just the same ring structure, but the same construction as Z modulo the ideal generated by 3. Really, they're conceptually the same thing. It's just Z mod 3 we sort of discovered through clock counting and not really initially by thinking about cosets of a subgroup. Okay, so anyway, in this case, our quotient ring is Z mod 3. Now just hold on to that thought. Here's another example. What if I take Z bracket X and mod out by that ideal that we talked about in the last video? I is the set of all polynomials a0 plus a1x, etc. up to an x to the n, where n is a natural number and a0 is even. And at this point, I'm just going to assume that we all know, since we're talking about Z bracket X, that all the other coefficients have to be integers. So the main condition is a0 has to be even. That is the constant coefficient. So in this case, we have, how many cosets do we have in this case? Well, there's 0 plus I, which consists of polynomials with even constant coefficient. And then that leaves one other ideal, 1 plus I. That's the set of all polynomials with an odd constant coefficient. And every polynomial has to fit into one of those sets. Either the constant coefficient is even or it is odd. So in this case, I have two distinct cosets. I have the ideal itself, and I have 1 plus the ideal. So in this case, the quotient ring, it's going to end up being Z mod 2, because really the ring structure on this quotient ring is just the ring structure on evens and odds, which we're already familiar with. That's Z mod 2. Okay, in both cases, I quotiented out by a maximal ideal, and what I ended up getting was Z mod something. Now, just by way of contrast, I'm going to give one more example. So what if we take Z bracket X and mod out not by this ideal that we had earlier with the polynomials with even constant coefficient, but what if we instead mod out by the ideal generated by X? All right, then what do the cosets look like? Well, there's always the coset 0 plus the ideal. That's just the ideal itself. So that's the set of all polynomials with constant term 0. And why is that? I mean, why is that coset the set of all polynomials with constant term 0? Well, what we're talking about here is the ideal generated by x. That's the set of all multiples of x. So any polynomial with a constant term of 0, we can factor an x out of it and treat that as a multiple of x. Okay, but if that's one coset, then what are the other cosets going to look like? Well, if I take 1 plus the ideal generated by x, then I'm taking all of the polynomials with constant term 0 and adding 1 to them. So that's going to be the set of all polynomials with constant term 1. Okay, and at this point, you look at this and you say, I don't think that we have covered all of the polynomials in z bracket x. I don't think we have a full partition yet. So we got to keep naming cosets. So we would have like 2 plus the coset, or sorry, the ideal generated by x, and we'd have 3 plus the ideal generated by x, and so on. And we'd also have like -1 plus the ideal generated by x, and -2 plus the ideal generated by x. All of these would be different and disjoint cosets. There's one of them for every integer. And it turns out that in this case what we get is z bracket x partitioned into not odds and evens, but into basically 0, 1, 2, 3, and so on. And then over here -1. And I'm being a little sloppy with notation. What I really mean is the class of 0 and the class of 1 and the class of -1 and so on. But this goes on forever. The ring structure I get here is the ring of integers. That takes a little bit of verification, but I'm claiming that the quotient ring in this case is z. All right, so in this case, what do we see? Well, when we quotiented out by an ideal that was maximal, we had z mod something, and in this case we quotiented out by an ideal that was not maximal, we got z. So I realize that this probably isn't quite enough examples to inexorably lead us to the following conjecture. I'm using my own knowledge to synthesize what we've seen here. But z mod 3 and z mod 2, these are both fields. And z, while it is an integral domain, it is not a field. Not every non-zero element of z has a multiplicative inverse. So what we will prove in the next video, I wanted to devote this video to examples mostly, and then focus on the proof in the next video. But here's a conjecture you might make. R mod I is a field if and only if I is maximal. And we'll prove that in the next video.